All right, everyone. I am here with Li Jiang. Li is a distinguished engineer at Microsoft working on Azure Speech. Li, welcome to the TWiML AI podcast.
Thank you, Sam. It's great to be here.
I'm really looking forward to digging into our conversation. You have had a long history working in speech recognition, generation, all different areas. Before we dig into some of the key innovations that you've been working on, I'd love to have you share a little bit about your background and how you came to work in the field.
Definitely. I was lucky to be introduced to speech recognition when I was an undergraduate student in mid 1980s. I had the opportunity to participate in research work as an undergraduate student researcher. I remember when trying to build a speech recognition system on Apple II computer. Uh, of course, the technology was fairly rudimentary, and at that time, and based on today's standard. But I fell in love with the problem space right away. It was simply magic to see computer can respond to your voice and recognize what you said. So I decided that this is the area I want to pursue. A number of years later, I was halfway through PhD program, focused on speech recognition, and I had the opportunity to come to do internship with Microsoft Research. That was a time the speech research group was just established. I love the experience and I love the company, and so much so that I stayed on and never actually returned to school. So that was 1994, and I became one of the first few people working on speech in the company. So over the past 27 years, I worked on the different roles and spanning both research and engineering side. So I did branch out into some other areas, but I was happy to come back eventually to speech field. Now currently leading the audio and speech technology as part of the Azure Cognitive Services. I was fortunate to witness not only the dramatic advancement in technology in the past few decades, but how the technologies are enabling people to do more and to improve their productivity. It has been a great ride, and I loved every moment of it.
Now, you mentioned the advancement in the field over the past few decades. What technologies were you working with when you got started in speech?
When I got started really early, as I said, I was in college, and at that particular time, it's just mostly the pattern matching, and one of the things is probably well known is called DTW, dynamic time warping. So essentially, try to sort of match one sequence with another. Then you have to handle that the different lengths. You have to sort of making sure that mostly dynamic programming type of technique to match the sequence really well to see how well it matches template. So that was the fairly long time ago though.
Hmm. And over the past few years, we've clearly seen a lot of innovation taking place through machine learning techniques. We'll be talking about that in a fair amount of detail. But I'm curious, how do you think about the progression uh, in speech through the course of your career?
Sure. Yeah, I'd love to share my perspective. Essentially, speech is the most natural way to communicate. So, using voice to interact with machine has always been one of the top scenarios associated with AI. So, since 1950s, researchers had started working on speech recognition. The earliest system focused on relatively simple tasks such as digits and numbers recognition. Technology-wise, as I said, the focus to start with was really on the pattern recognition and the rule-based expert systems. So it was the statistical approach with hidden Markov models that really created a new era and served as a foundation for modern speech recognition systems. The HMM framework resulted in major breakthroughs and enabled accurate recognition of large vocabulary, speaker-independent continuous speech. Prior to HMM, there was always some kind of restriction, such as you have to do isolated speech, or it's small vocabulary, or speaker-dependent fashion, and it's really the HMM framework helped lifting all those restrictions.
And HMM being hidden Markov models.
Yes, yeah, that has been a dominant technology prior to deep learning era, and even today, I think with the deep learning, I think the some of the HMM, such as the decoding framework and other things, is still sort of the same as used in the HMM era there. So towards 2010, deep learning started showing promising results for speech recognition. The early work using feedforward DNN demonstrated its power with significant improvement accuracy over HMM. So essentially, by replacing the Gaussian mixture, sort of probabilities with the sort of output of the DNN network, I think that really has been a major step forward there. So the neural network models are not only very good at memorizing it, and it was able to model the longer context much more effectively. And for that reason, I think it actually generalized much better. So since then, there has been rapid innovations in different model architecture. The LSTM model was found to be very suitable for speech, and it became the newer generation of the models that further improved the performance. So more recently, transformer models, which originated in NLP, has really shown promising improvements across different fields, including speech. So another important development when it comes to speech recognition is really the end-to-end architecture. And until now, I think even today, for cloud speech recognition system, we still have, and most people do, still have the separate acoustic model, language models. So in the last few years, the end-to-end speech recognition models have got a lot of tractions, a lot of investment and research work there, meaning a single model can take speech in and it just output text results. So essentially, the single end-to-end models are jointly modeling the acoustic and language aspects. So the end-to-end architecture is particularly suitable for devices as its memory footprint can be 100 times smaller than traditional architecture, and accuracies could be sort of on par or roughly the same. Uh, so without a so without a doubt, in summary, the deep learning has had profound impact for speech field. As an example, Microsoft first actually reached the human parity on a very challenging switchboard task in 2016, thanks to deep learning technologies, and it was a historical milestone for AI. So,
Can you describe
yeah,
that switchboard task a little bit?
yes, switchboard task is a well-known and the data set and task and for speech community. It was collected by NIST and LDC, and essentially the data set was sort of collected to so the research and the community can tackle the conversational speech and the problem. So what it does, how it was collected was to have two people talk with a selected topic, commonly agreed topic, and selected from a range of topics, and then they just carry a free form conversation. For example, the topic could be talk about credit card, talk about finance, and some other topic. So it's a really free form conversational speech. It's a very challenging task because of it's not script and it's not a read speech. It's just a spontaneous conversational speech. It has a lot of disfluency effects, has such as hesitation, false start, repetition, filler words, everything. So the telephony channel, of course, added even more difficulty to the task. So I think over the past 2 decades or a few 2 decades or so, I think when people started working on this has very high error rate, probably starting with 20% and then down to 15 to down to 10-ish. I think in the October 2016, and Microsoft reported that the two results. One of them is we had a professional transcribers trying to transcribe that, and for even for human being, the accuracy, the error rate came as a 5.9%. Then the system with the deep learning can actually was able to achieve 5.8. So that was essentially reaching the same ballpark of the performance as human. Of course, I mean the other teams, organizations, and also work on this. So they point out saying, well, if we have multiple human, working as a team, then human can actually do better than 5.8. It's true, so that they essentially with the multiple people working on transcribing over cross checking and validating, they can get down to 5.1%. Essentially, there's still 5% ish error rate, and even for human. So I think after a year or so, in around August 2017, and with further work from the Microsoft and the system was able to reach 5.1% again, once again reaching the human parity, even with the multiple human team up to do the human transcription there.
Hmm. When we're talking about error rates and human parity as the benchmark for these types of tasks, is there any work that's been done to characterize the types of errors? I'm envisioning, for example, humans might make errors that, preserve the meaning. Just in their heads, they kind of substitute out words, but they don't change the meaning. Whereas machines might make words that are more impactful from a perceptual perspective or from a meaning perspective. Has anyone looked at that?
I think there might have been some of the work in for the analyzing the results, the error types, and I agree with you that for human and machine that might be making different type of errors. But when you get into the 5% range, I think most of the errors based on my analysis of the some of the very sort of brief looking over the errors. A lot of those is because the conversational nature of the senses, even for human, it's not obvious and what that particular word is, and so it's uh, so for computers it might be sound like mistake, and for humans that might be it also sound alike but a slightly different form. So I think it comes down to probably not a hugely there's not a huge pattern and to be clear says what type of error it is. It's just a certain portion of the speech plus the channel noise make it really hard to be intelligible to even to human being.
Okay. Okay. And you've talked a little bit about this transition from kind of this hybrid model where you've got a separate model for the acoustic channel and a language model to a end-to-end trained model. Can you elaborate on the kind of the pros and cons, the challenges of the each of those different types of models?
Yes, definitely. So I think that the traditional architecture, essentially, we have that's mostly widely used one, and is has a few of the decoupled models. Essentially, we have acoustic models that trying to sort of model the acoustic events, essentially trying to tell which particular phonemes you're producing a sequence of phonemes. That's the role of the model. Then we have a language model that is trained. The acoustic model is trained on, tens of thousands or hundreds of thousands hours of the speech and the labeled speech data. The language model itself is trained on the text. It could be trained on billions, hundreds, billions, or even trillion the words. And essentially, for our language model, is literally trained on trillion word corpus. But it's a text only. Essentially, trying to model the, if I have uh, if I see this sequence, then what is the next word would be? And then of course there's a pronunciation that connects the acoustics and the word and together. So essentially we have a three major part and acoustic model, language model, pronunciation model. It has been achieving, a great accuracy performance and it works well. The the downside of that is the memory footprint is actually huge because the language model tends to be, it takes a number of the gigabytes and the size, and you can compress, you can sort of construct the graph and FST and with the language model and in highly compressed binary form, but it still takes the multiple gigabytes in order to be able to do the search and the decoding over the graph. Um, but the benefits of the pros and the biggest one is this decoupled architecture. You can train the language model. You can decouple, like you can train the language model from trillion, hundreds billion or trillion words, that is really flexible, that you can sort of use more of the text data to train part of your speech recognition model. And the biggest benefits is you can easily customize the model. For example, if you have a new word, tomorrow there's a new sort of terminology comes in, you can just modify, tweak your language model very slightly. You can add a new word, you can add a pronunciation, and now you get it. And in the system, instantly you can have it. So um, the end-to-end model has been really the trend, the new trend for the community. Has been a lot of effort, and the putting into this area has been a huge amount of progress over the past 2 to 3 years. So in terms of accuracy, that it's more or less can match the hybrid model, and the biggest benefit is really really small and compact. Essentially, you have one model. You don't have no longer have the separate models, and you can have the model that is small enough you can fit into smartphone, and you can or even IoT device, and a fairly small size, and you also get a very very accurate recognition of the model. So the biggest problem, I think, with the end-to-end architecture as of today is still the ability to customize and to modify. And if you, for example, the same problem, if you have a new word, we want to add that new word into the system, you have to almost without we don't have a technology we can easily insert a new word into the system, and you almost have to somehow and uh, sort of getting that data and to retrain the entire model in order to for it to recognize this new word. So this flexibility is the biggest issue that the community is still working on. And so another thing is that since we no longer can train the language model separately, because all the acoustic models, language models, are folded together into a single model, and then your data is even more sort of have a bigger dependency on the speech labeled speech data, and the speech. So the data amount and the data coverage becomes a much problem. If your training data has never seen a particular combination, for example, in order to recognize even all the numbers or the names you have never appeared in your training data, it's harder problem for the end-to-end system and the models to be able to cope well with something it has never seen before. And so for that reason, I think there's a still good amount of research work and to focus on the area.
And that's in contrast to a hybrid model where in it may have not seen the word before, but it's heard the sounds and knows the phonemes and that kind of thing.
Yes, and the especially because you can train the language model. Language model can cover hundreds of billion of the words in the context. So that
Hmm.
gives you the context that you don't necessarily have that in the labeled speech data. So essentially, that aspect is the one that is still
Mm.
sort of having advantage over the end to end, which you can only use you. Its advantage is also disadvantage. You can only use the sort of speech label, speech data that to train the end-to-end model. You can at least there's a research work on that to use the separate text data to enhance the model, but that has so far been more of the research topic.
Hmm. Hmm. Your earlier point was that these end-to-end models are more compact than the hybrid models. That's maybe a little bit counterintuitive because we think about these, these transformers as being relatively large and heavyweight from an inference perspective, a deployment perspective. Can you elaborate on what makes them more compact? Is it just that the former, you've got three models and
Yes.
okay.
Yes, correctly. And mostly the hybrid models, the reason is huge is the language model itself. So language model, and um, there are actually two types of language model, and over the for past few decades, the so-called n-gram language model has really been the backbone of speech recognition. And even as of today, in the hybrid model, the n-gram model still is the backbone. And the reason is the n-gram models is essentially it's a statistical model. You just basically count the co-occurrence of the words together. You can have different orders of the n-gram. And when n equals 1, you get a unigram. N equals 2, you get a bigram, trigram. N equals 3, trigram, so on and so forth. And the benefits of the n-gram models is it's really, really efficient. And both in terms of training and also in terms of the runtime decoding. But the speech, because it's a sort of high dimensional, timing sequence, and the real time recognition and decoding is so critical that we can't really wait for. So that basically makes the n-gram to be the sort of unique choice, and still as of the sort of choice for us today in the first pass, what we call the first pass decoding. So that language model, the n-gram language model, is typically tens or hundreds times sort of bigger than the acoustic model itself, because you have to memorize how many words followed by some other word sequence. You have to basically sort of store those things together. As I said, that there are ways to compile into a graph and a very efficient implementation, but even with that, the majority of the size for the cloud hybrid system is really on the size of the language model and the decoding graph. So with the end-to-end models, we no longer have that sort of decoupled language model. So essentially, language model is followed as part of the end-to-end model. It's a transformer. The encoder we can use recurrent neural network. It's RNT, or it could be transformer. And then we have something called a transducer sort of architecture. Then you have a so-called a language a prediction network. Is equivalent to the hybrid language model, but it's just LSTM, and it's essentially it's relatively straightforward, a small size, and you have a unified sort of network, and combining them together. So the overall model is not much bigger than the encoder itself, and it's probably could be comparable to the acoustic model in the hybrid architecture, but without the n-gram language model itself. That's how the size can be so much more compact and so much more smaller.
Got it. Got it. And then the next challenge you mentioned was that of customization. And you mentioned that as a open research topic, but I, I do know that as a service on the Azure side, as you're trying to deliver this, folks will want to customize their speech recognition systems, bring their own words, or bring their own label data, and you do accommodate that in some way. Is that right?
Correct, correct. When I talk about the customization for end-to-end model is still a research topic. That's why the end-to-end model is still not being used for our cloud service yet.
Ah,
So
okay.
I think that's probably true for most of the other providers. So right now the end-to-end model has been released to be on the device on the edge, but for the cloud, I think it still lacks some of the flexibility I mentioned. So for the customization, I do believe that is a very critical capability and feature for a lot of services. The reason is for different domains, for different scenarios, and for even for different companies, and there are so many of the sort of terminology or jargons or technical terms, or some of the things very much related to a particular application scenario. And even though our generic system performs pretty well, and it's still challenging when it comes to those different entities, which is domain specific. So having ability to customize the models and for particular application scenario has been very important. So for Azure Speech Service, we do offer this capability that we offer the platform. Like you can bring your own data, you can upload your text data, depending on how aggressive you want to do, you can start with the language model. You can upload your text data corresponding to the content and mostly applicable to your scenario. Then we can use that to customize language model only, or when you have an application that is very large scale application, you have acoustic data, you can also upload the speech data. Then we can use that to customize the acoustic model. Of course, we can customize the pronunciation as well, fine tune that, and we provide a studio that you can essentially experiment. You can run the evaluation against your own data, then making sure the new model is doing better, and before deployment, so on and so forth. That has been uh, very sort of we feel like that's a great feature for the customers to have them application have their application working really well.
Hmm. Hmm. And is the focus of your from a service perspective? Are you focused on kind of very broad and common language, or are you also going to popular domains like say medicine or finance or law, things like that, and proactively kind of building out your data set to incorporate more and more of that specialized terminology?
That's a great question. I think for our service, we aim at fairly generic scenarios. So we build our models and with as broad a data coverage as possible. And we uh, always, when we do the evaluation, we do the testing, we test against a wide range of scenarios and applications, making sure that works relatively well. So we do offer the customization feature because we feel like that is the additional feature and the capability that we can offer the customers by having a means for them to participate in this customization. And also another reason is like we don't see the data when after they upload the data, and they control the data, they control the model, so it's their part, it belongs to them and the rights. And so that's the way we address it, how we having the sort of platform capability to make our models and being improved, being fine tuned, and the optimized towards application. So there are different domains. Some of the domains, for example, finance domains is probably does not, the sort of some kind of optimization would be sufficient because it's still generic enough. But medical domain, for example, is as an example, is going to be much harder for the generic models to perform well. And that's because the medical domain has so many of the sort of terminology, and even for me, and a lot of those words are totally unknown to me. And
Hmm.
that does require much deeper and investment and nuance. Actually, it's well-known. Nuance has been a leader in that space. It has really spending uh, lots of investment and with a lot of experience in handling medical domain. So that's also part of major reason why Microsoft decided to acquire Nuance. And I do hope post acquisition and what we have and what Nuance have, and we will be able to leverage each other and really being able to providing that the solution uh, both in terms of generic capability and also some of the domain specific, especially when it comes to the medical.
Hmm. Hmm. Yeah, I think we think about um, artificial intelligence from a very um, kind of common mass market perspective. You think about the system that you train on some data, you teach it some stuff, and then it learns, and then you collect some more data, you teach it more stuff, and then it learns. And say you've got this broad set of capability that you've collected a lot of data about common speech, you've built this model, and then you might think, hey, let's go find another domain, teach the same model about this other domain because we've collected more data, and then we think a bit of it like how we learn. You keep stacking, and as you learn things, it doesn't necessarily degrade the performance of the base level things that you've learned. But is that the case for the kinds of models you're working with? Like, or would you always want the to kind of segregate the knowledge for the different domains? Because if you try to do tasks, generic tasks using something that's trained on the medical data, you would introduce, maybe more errors with your model.
I think that's a great question. I think there are different ways to deal with different domains and verticals, and my personal view is there's no black and white. I think the generic models is going to be sort of being worked on and is going to be improved constantly. That yeah, there's been great progress. If you look at the track record and the models that is becoming more and more capable, is becoming more and more powerful, and with the essentially more data coverage, I think that the models can learn to deal with different domains and different applications, different scenarios, so that generic capability keeps improving in the until this model is adequate for all different applications and different domains and different verticals, there's always some of this domains might need more of the sort of improvement or specific customization or optimization in order to satisfy the sort of workload and the workflow and particular requirements in terms of performance. I think a medical domain is one of those sort of on the extreme example because it's one of the hardest domain, hardest the vertical in order to get it right, in order to get that adequately good enough to be used by doctors and medicals, the workers there. So I think there's going to be a two-leg approach, and while we try to improve the generic model capability, and there's always going to be some kind of need until that generic the model being good enough and for that particular domain. And of course, I mean, a lot of things is really looking. If you look at the machine learning, look at the deep learning, a lot of things really depending on the data and how the data how much coverage you can get and how you are able to train the data. Is that architecture going to be flexibility sort of flexible enough to really incorporate all the knowledge and the information and embedded in the data? And when the technology keeps improving and the more data, the more sort of training becomes effective, being able to really extract that knowledge and the information and embed it into part of the model. I think gradually, eventually, I believe that the model is going to be good enough to handle almost all the domains and scenario. But in between, we have to take a pragmatic approach and saying. How can we make this technology working as well as we could for all different applications and domains?
Can you talk a little bit about the trade-offs between delivering a certain level of accuracy or quality and the kind of runtime characteristics that you require as a service provider? You've talked a little bit about this in the context of hybrid versus end-to-end models, but tell us a little bit more about kind of the engineering aspects of delivering a service at the scale that you're operating.
Absolutely, and I think the as a service provider and providing this cloud and edge service and for speech recognition and text to speech and as well. I think a major challenge is really how to we be able to really get in the latest and the greatest technology and the innovations in the science into the production, into the service, and also really shorten the cycle of the once the technology is capable that how we can get that into into the service. One particular example I would probably use is really the text to speech. So far I mostly talk about speech recognition, but text to speech is also has had an amazing journey, and coming from the previous technology into the deep learning, and so I think a text to speech, and prior to deep learning era, it was mostly concatenative system using unit selection, and it has pretty good the sound quality, but you have to store a lot of voice samples, and in different contexts that adds up to a huge amount of the storage, and also you have to record a professional voice talent, and you basically have to sign a big long contract with a voice talent, and then you can record all the samples, and sometimes takes months and a year to record enough samples to be able to build a system, a sound that can cover all the really sort of great and the quality. So I think in 2016 it was the WaveNet and Tactratone too, really sort of pioneered the end-to-end speech synthesize, and that sort of having that new TTS being able to sound a lot better than really close to human quality. And another benefit is like a newer TTS actually reduce the entry barrier on the data recording, because it can leverage a wide range of the data. We no longer need a single voice having in many hours. So we still need some in order to fine tune, but essentially we can have a pre-trained model with all this data coming from same data used to train the speech recognition system, that we can pre-train a big model, and then we can fine tune that to a particular voice, that getting us really sort of close to human quality. But one of the things that when that comes out, I think it's just super slow, because it's a autoregressive model. Then it's a sequential. The inference, everything is really slow. You do need sequential basis. You get one sample, and you produce one sample, then you produce the next sample. In that fashion. So I think a lot of work is for neuro TTS was to really saying how we can get this amazing technology into the service, and still sort of with a reasonable cost, so we can actually sort of productize the system. So there's a huge amount of work being done there. There's a couple of things. One of them is really from modeling sort of from technology point of view. Can I have something sort of roughly given me the same performance, and but much more faster, much more simpler, right? And um, that's one thing. The second thing is, how can we being able to distill knowledge? Typically, that's a lot of common techniques being used is a, teacher-student model. Then you can have a teacher model which is much bigger, and it could be the sort of auto-regressive, but then your student model could be much more compact, and it's you can run in parallel, and that's a common technique we use. Then so of course there's other sort of common techniques and to make the model smaller. For example, you can do the quantization. 8-bit is a typical standard that you can even do go further if we're willing to sacrifice the sort of precision a little bit. And there's also some other techniques such as the SVD. Then you can basically decompose a big sparse matrix into multiplication of the smaller matrix. Then you sort of compress number of parameters, and all this since combined together, that's how we being able to get the new TTS into our service. And we want the first one, or one of the first one, to get a new TTS into our service stack, and being able to have the cost and the latency coming down by even hundreds of times, and to really make it a realistic offering for the customers. And we also feel very good that we're able to add this customize the new voice capability into our service. And we have had some of the really happy customers being able to build their own brand of voices, and with the characteristics they want. For example, AT&T had this Bugs Bunny voice, and they really use that to sort of being able to engage with the customers. So that's a that's an example on the text to speech, but for speech recognition, it's more or less the same. And some of we have to every new model comes into showing a better accuracy. I think there's a lot of work being done to make the inference faster, to make the model smaller, to make a latency, not sort of being more than it used to be, or even sort of with an improved latency. And that's a big part of the what we have to do.
Great, great. What kind of uh, data collection or data coverage does a customer require to customize a voice in the neural TTS service? Is it a lot of data, or is there a high degree of transfer from the base models to the custom model?
There's a very high degree of sort of transfer from the base model, essentially the pre-trained model we have, and I think we probably to get a decent quality of a customized voice, you probably need to spending uh, you know not a whole lot. I think it's probably a few hours of the data in order to getting a really high quality customized voice. We also internally we also experiment with the personal voice. Actually, I have a
Hmm.
personal voice font for myself. I
Okay.
just spent about 30 minutes or so, and recording some of the with some prompts, recording some voice, and I get a fairly decent quality and personalized voice font that we've been using that playing my own email, and it's really kind of interesting and to hear your own voice and sort of reading your own email, for example, and that's it's kind of a very interesting experience.
Can you talk a little bit about the cross language aspects of what you're doing?
Yeah, definitely. And yeah, a lot of the mission, I think we have a mission is to really having our technology helping to break the language barrier, and of course, together with the machine translation, and essentially, we want to be able to cover as many languages as possible, and the uh, for sort of rich resource language like English, the data is coverage is not a problem. We have plenty of data. Of course, the more the better. But when it comes down to the sort of smaller language, I think the data resource becomes a bottleneck, and there's low resource languages and fairly challenging that in terms of the really getting same amount of data or same quality or same coverage of the data as we have with the rich resource languages. So that's when we invest a lot in transfer learning, and what we do is we want to really combine the knowledge that we have across many different language that we build a multilingual the model that to as a pre-trained model that we can therefore use that model we can transfer do the transfer learning and being able to sort of fine-tune that with a very small amount of data for the low resource language that we be able to build a good quality of the model. And some of the times is the interest finding as part of work is even for some certain language that we don't think we have pretty good amount of data. For example, Italian, we do have pretty decent amount of data, not as much as English, and but it's still good. What we still find is this, the transfer learning and is we are able to leverage the English the data. If we build this, if we take an English model as a base model, then we do the transfer learning with the Italian. We actually being able to see the better performance, better accuracy with Italian language. So I think that was eye opening, saying like even it's not a sort of tail end towards the really small, low resource language, that the technique, the transfer learning is can be very powerful. And if we can pull all the resource across many different languages, then we're able to sort of leverage that the information knowledge and in different languages to benefit others. So right now we offer the speech recognition for more than 100 language and the locales and dialects. And same thing for text to speech. We have 70 languages, and we are adding very soon. We're going to add in more to reach 100. Language in the dialects and the milestone, and this of course our goal is to actually getting even more, so we be able to have that coverage and be able to help people to as doing what we need they need to do to getting higher productivity to do more the things they were not able to do before.
Hmm. And now, if we connect some of these things that we're talking about, and say I wanted to do a custom voice font for Neural TTS that I can use to read my email in Italian or something like that, do I need to record the data in Italian, or is there a cross-lingual aspect to this?
Yeah, that's a great question. Yes, and we actually recently released a few months ago. We released this capability that you can customize and the voice and without speaking another language. Essentially, if you can create a voice, we can create a voice font for you when you with some of the samples from you reading English text, then we can create a font with cross-lingual transfer learning, and we can actually get you a font that you can speak Italian, you can even speak Chinese, and if you want, and or the other language under your choice. So that's all benefit from the deep learning technology that we have the acoustic model of the TTS that is trained from many of the speech sort of speakers and the thousands of the speakers. We trained from tens of languages, and it's cross-lingual in nature. And also another thing we can transfer learning is not only sort of the language, but also the style. We can sort of have a different style depending on the application. You can say, wow, this is a happy sound, and or some other styles, and that's some of the work I think is all part of the investment in deep learning technology for TTS for customization, and we continue building on that.
And so the style there, it sounds like it's not just a kind of a cadence or speed or something like that, but also emotional content. What are some other examples of styles in this context?
I think that we have, yes, it is the emotional aspect and of the styles, and we can the styles of course has multiple aspects. I think this particular we can have for example, the happy and sad, and that will be examples of the typical examples of the emotional styles. And we are also looking into some other sort of vertical domain. For example, we know for the news anchor to read the news, that's fairly different from some other, for example, personal assistant. That personal assistant, you want it to be relatively warm and cheerful, and for news anchors, you want it to be relatively calm and sort of, feel like, that's a source of the authentic news, right?
Mhm.
So those are the things, and of course, how we have a few choices and in our service, and right now I think that's something we continue working on to see how we can being able to have the even richer offering in terms of the voice fonts, and many of the different voice fonts you can pre-select, and also different styles, and that for customers to choose from, for so to best match their application, their purpose.
Now, thinking about things like voice fonts and neural TTS also calls to mind dangers like deep fakes and the like. How do you manage um, your responsibilities there?
Yes, that's a great question. That's something that is really high on our radar screen, and I think we deeply believe that while we do have a lot of horsepower and in terms of technology, but being able to uh, offer that technology, offer that service, responsible manner is the top priority for us. And so, deep fake is certainly a problem when the when you get, for example, we are able to create the voice that is so um, sort of sound like a real person, and that but we have to be super responsible that making sure that it does not fall into the hands of the sort of malicious users and trying to use that voice to do something, and that not intended for. So we have dedicated responsible AI team, and we also the Microsoft as a company also have the sort of the particular team, and working on this and making sure that the technology is sort of being used, the AI, and being used in a responsible way. So particularly for the new sort of voice that is that we can customize, and we have a rigorous process, and we have a gating process, so it's not open to it's gated, meaning you have to apply for that, and we have a review process that we making sure that we understand your scenario, we understand who you are as a customer, and that's a screening, that's gating process. In addition, we also have something we call the liveness check, and built into part of the enrollment, and so we make sure that, for example, if we build a customized voice for you, you go to the site, and we have a process, and we make sure we want you to read a particular prompt, and making sure that the voice is coming from you, and instead of you cannot uh, sort of copy someone's voice from the internet, then you start to register and trying to create a voice. That's not allowed, because a liveness checker is going to catch that, and you will not be able to create something that on behalf of other people. uh, so those are the some of the ways that we've been implemented as part of service. In addition, we are actively working on other things. For example, we're working on the watermark feature for our newer TTS, that we be able to offer a unique watermark that we can detect, and for whatever the voice and the font we release, we'll be able to reliably know that's generated by our new TTS, and we can also offer to the other people who want to check, and if it's the voice generated by us, and that those are the some aspects we're working on, and again, this is top priority for us.
Awesome. Uh, where do you see the future going for these kinds of services?
We continue improving the technology itself. I think there's still a lot of work for us to do, even both for speech recognition and for text to speech. I think the technology has really come into a point that is that uh, it can power up a lot of scenarios, and we have that power up many of the first party applications such as Teams, Office, and PowerPoint, and Microsoft Word, and we also have many of the external customers, and including the AT&T, including the Tesla in China, including the Samsung, and Allstate Insurance for call center, everyone. But I think there's still a need of to improve the technology, and for speech recognition, for example, we need to make it much better in terms of the entity and being entity aware. Sometimes we get a name, and it's hard to recognize, because the sensors are hard to recognize what the particular acronyms or some other terminology jargons and things like that. So those are the aspects, and we have to adapt. Sort of really making the increased bet to improve its capability. There's multilingual. There's code switching, for example. Sometimes we find that for particular application for different language, for example, because there's always a mix of the English and other language together, so that code switching is a hard problem, and we have to solve that better. We have to make the system much more robust, and being able to be portable, meaning from domains to domains, and from different channels, and from different applications, and it needs to be really, really robust. For text to speech is also similar, that we have the way, for example, when you have a non-paragraph right now, for single utterance, it sounds really good, but when you have trying to read an article, read an email, that it has a long context and haven't. It also has an entity problem. Sometimes it does not pronounce a particular word or name correctly, or sometimes you have this contextual thing, and with a long article and the email, that you have to be able to have a better handle of this context and the with the long article. All those are the technology sort of the improvement that we need to make it even more closer to the human, close to the human parity, not only in a particular domain, but generically just across the board, being able to getting closer and closer to the human capability there. And then of course landing that with the more and more applications and customers, and it's always the case when you apply technology to a particular scenarios. That's what we learn the most, and it's like we learn the system is not doing well in this particular aspect, and for that particular application, those kind of learning are really helping us to be able to keep improving our fundamental capability, and the only ways to sort of really having more customer and being able to work better with the customer scenarios.
Awesome. Awesome. Well, Lee, thanks so much for joining us to chat a little bit about what you're working on and innovations in the speech recognition and text to speech areas.
Thank you so much, Sam. It's my pleasure.